All right. So today kind of brings together our two concepts of delta H and delta S, our enthalpy and our entropy. For this entire unit, we've been talking about how we can calculate enthalpy. And as chemists, we are very interested in the amount of energy that is released or absorbed during a chemical reaction. Yesterday, I introduced you to a term called entropy, which is a measure of how disordered a system is. It's also a measure of how much actual work a chemical system can do. And I say a measure because it's actually a combination of the delta H and the S. But this is a good enough introduction for you guys. When you encounter this topic in university, you'll get a more deeper explanation, which is fine. I don't have nearly enough time to actually go into the depths that need to be done to truly explain it, but it's good enough. Entropy is a measure of how disordered a system is, and it's also kind of a measure of how much work it can actually do, all right, like pushing a piston or moving something. What we want to do now today is talk about what makes a chemical reaction spontaneous. And we've never really talked about that before. We've just kind of assumed it. If you put chemicals together in a reaction vessel, either the reaction can proceed and a reaction happens, or the reaction cannot proceed. It just sits there. It doesn't do anything. We've seen successful and failed reactions before. We've seen them in single displacement reactions. You put together the right metal with the right compound, and if you use the activity series, you can then determine whether that particular reaction will take place or not, whether it goes on its own, whether it's spontaneous. But if you have a different metal that is already alone, that wants to be alone, we know that that reaction won't take place. We would call that a non-spontaneous reaction. It just doesn't happen. And so what we want to talk about now is what determines whether a reaction will be spontaneous or whether it won't happen and be non-spontaneous, all right? And we have the tools now to make those predictions for any chemical reaction. As long as we have our thermodynamic data, we can make those predictions. Let's first define a spontaneous reaction. What a great statement. Reactants become products. Well, of course they do. That's what a chemical reaction does. So it seems kind of silly that we have to define it, but I guess the first one is the most important part. It occurs without continuous outside interference under a given set of conditions. An example of a spontaneous reaction, and this one will come up in this discussion, could be H2 gas, like in the hydrogen balloon, with some oxygen gas, all right, to produce some H2O, and we'll put it as a gas in this case. And I think I need a 1/2 in here to balance that up. Now, if I put a little spark, and by putting a spark, that's not continuous outside interference, that's an initiating bit of energy. We'll talk about that later. That's different. The spark is needed to get the reaction initiated, but once the spark is there, I don't have to continually add heat to that reaction. It feeds itself, and the hydrogen burns, and the hydrogen balloon explodes. So that's not continuous outside interference. Given the right conditions, hydrogen and oxygen will combine to form water, and it will do it all on its own. That is spontaneous. All right? Non-spontaneous reactions. It doesn't occur without outside interference. Seems pretty obvious. reactants do not become products. And a non-spontaneous reaction example is just the opposite of what I used as my example for spontaneous. Right now in the air in this room, there's water vapor, right? There's some humidity. That's water vapor. That means that in the air right now, there is H2O gas. And that H2O gas is not spontaneously breaking down into H2 gas and O2 gas. It's just not happening, all right? Even if I put that spark, right? If I had my lighter, I've lost my lighter. I need to find my lighter again. We'll do the thumb lighter. Even if I had a lighter and held it out in the air for all that water vapor, that's not going to take place, all right? We can make that reaction happen under certain conditions, but I need continuous energy input. If I were to put the water into a Huffman apparatus, which you might have seen in grade 9 and grade 10, and we put the electrodes in there and we plug it into an electrical device and we input electrical energy, we must continuously input electrical energy to rip those atoms apart. So we can force it to go, but without outside interference, it won't go. We call that a non-spontaneous reaction, all right? We can come up with physical examples of spontaneous and non-spontaneous. You have a rock on the side of a hill, you let it go, it rolls down the hill all by itself. That's a spontaneous physics or physical interaction. It rolls down the hill. Rocks roll downhill. Pretty straightforward statement. They don't just roll uphill on their own, but you can get them to roll uphill. You just need some continuous outside interference, someone who wants to put in the effort to roll the rock back up the hill, but they don't spontaneously roll uphill. This is a similar idea. Certain reactions happen on their own, and other reactions don't. They need some help. We want to be able to predict what makes one spontaneous and one not spontaneous. You don't write this down. This is just examples of some spontaneous reactions. Like I said, if we have a single displacement reaction, all right, check the activity series. Silver wants to be on its own. Yes, it takes place all on its own. No effort needed. Silver with some copper chloride. Silver wants to be alone. It is alone. That reaction doesn't happen. It's non-spontaneous. So we have all kinds of examples of spontaneous and non-spontaneous reactions. You can write this down. So what makes a chemical reaction spontaneous? Well, there's two reasons. There's two factors, and it involves enthalpy, delta H, and entropy, delta S. The first one we'll talk about is the enthalpy, which is essentially that energy that's stored in a chemical reaction. I've already given you one reason why a reaction happens spontaneously, and it comes down to the statement, rocks roll downhill. It always happens. In terms of gravitational potential energy, an object that has high gravitational potential energy will always eventually move to a position where it has lower gravitational potential energy. Asteroids fall from the sky, rocks roll downhill, what goes up must come down. Those are all examples of objects moving to lowest energy, lowest potential energy. That's true for a chemical reaction as well. Remember, enthalpy is kind of like a measurement of the stored energy in a chemical system. It's the energy in the bonds. It's potential energy. And so just like in a physical system, something of high gravitational potential energy will just naturally proceed to lower gravitational potential energy. A chemical system of high enthalpy will naturally proceed to a system of lower enthalpy. And when we have a system going from high enthalpy to low enthalpy, we say it's a negative delta H. We say it's exothermic. Exothermic reactions tend to be spontaneous. And notice I said tend, because there is a second factor that affects this. Chemical systems react to minimum enthalpy. Rocks roll downhill. It's the same thing. The universe, for some reason, whoever designed it, going down a theological path. I'll stop. Whoever designed the universe has it built into the universe that things of high potential energy naturally settle down to situations of low potential energy. Rocks roll downhill. Fundamental law of the universe. We see it everywhere. So if we have a chemical reaction that has a negative delta H, it's exothermic, then it has the potential to be spontaneous. Now I've got a next slide here that illustrates this, not illustrates it, but kind of fortifies it. I'm just, thinking ahead to where I want to be at the end of class. I don't think it's necessary to write this next slide down. Let's just take a look at it, and we'll be critical about it, and then and decide whether it's important to write it down or not. This is the important part here. Chemical systems react to minimize the enthalpy. Delta H's that are negative, the universe likes. The universe drives that reaction forward. So this next slide here, I've got here, chemical systems naturally proceed to minimum enthalpy. I think we've expressed that. A reaction is spontaneous if the enthalpy of the system decreases, if the delta H is negative, so high enthalpy to low enthalpy. A reaction is non-spontaneous if the system increases in enthalpy, in other words, a positive delta H, and there's my does not proceed. I think we get that idea. I don't think we need to write that down. If a reaction is exothermic, the universe likes it. It has the potential for being spontaneous. So let's just move on to the next part of the idea, and that is the law of entropy. We've seen entropy. It's a measure of disorder. It's a measure of how, disorder, chaos is a word we sometimes use, chaotic, disordered, a chemical system is. And it turns out that chemical systems naturally proceed from a state of order to disorder. And I had a statement for the entropy slide that you wrote that I think said chemical systems proceed to a state of minimum enthalpy, or they decrease the enthalpy. And so I'll add that same statement to the bottom here for entropy. Chemical systems proceed to a state of maximum entropy. All right? So if a chemical reaction can have a delta S that's positive, for some reason the universe likes that. Yesterday I went on a tangent how scientists believe, or they theorize, that our perception of time is based on this law, on how we perceive things going from ordered state to disordered state. And then I went on a crazy tangent about all points in time existing simultaneously. It's very intriguing. If you want to continue that discussion, come at lunch. Mr. Petrus disagrees with me over many campfire discussions. So two laws that govern spontaneity. Minimum enthalpy, negative delta H, maximum entropy, positive delta S. And we know how to calculate both. So that's where we're at. We're simply going to be doing some examples now where we calculate the delta S and calculate the delta H, and we make a decision. Is this got the requirements for spontaneity, or does it not? And as you can imagine, there's going to be three type of situations we can have. We can have the enthalpy go down and the entropy go up, spontaneous. We can have the opposite, the entropy go up and the enthalpy go down, non-spontaneous. The universe doesn't like that. But then we've got two intermediate situations. The enthalpy goes up, universe doesn't like that, and the entropy goes up. Oh, the universe likes that. And then we've got this competing situation, or down and down. And those middle guys, those ones that are either up and down, have the ability to be spontaneous at one temperature, but not spontaneous at another temperature. So there's this switchover temperature where spontaneity can take over. So those are the situations we want to discuss. So, very simple thing you keep in your mind, those two laws right there. Again, in chemistry, we like to have little tiny sayings that help us get through. What did we have last year? Did we have any silly little sayings? Did I go over any of them? At the end, well, for electrochemistry, we have oil rig, right? But we haven't learned that one yet. I'm trying to think. Did we have a silly saying? Yeah. Oh yeah, ikai high, so low. Excellent. It's a good one. Ikai high, so low. And this one here, minimum enthalpy, maximum entropy. The universe likes reactions to have move to minimum enthalpy, negative delta H, and move to maximum entropy, most chaotic system. All right, let's look at some examples. Hold on, don't write this down. We're going to actually, hold on, let me see what I want you to write. Yeah, I do want you to write the top part, but don't write the examples. Don't write the examples. Just write the top part. A reaction will always be spontaneous in the forward direction if it is exothermic with increasing entropy. So here I've got a quick little table. If I put my enthalpy and I put here at positive and negative, and my entropy as positive and negative, we can then kind of find the spots where we're going to have spontaneous reactions or non-spontaneous reactions, all right? So in this case, positive delta H greater than 0, negative delta H and positive delta S. If the delta H is negative, that's spontaneous. And if the delta S is positive, that's spontaneous. So this is always spontaneous. So this is always spontaneous, all right? If we were to maybe put check marks where the universe likes it, the universe likes this, but the universe doesn't like that. And the universe likes this because it likes chaos, but the universe does not like that. So the universe likes this and likes this, always spontaneous. All right? Some of you may even like this idea better than even writing all this stuff down, right? This is a little more graphic of a representation. If we need a legend, right? I don't want to put spontaneous, but the universe likes this, right? I don't even want to maybe touch that, right? Because spontaneity depends on both. I can't just say check mark is spontaneous. I could say check mark is spontaneous with respect to that particular thing, like the delta H or the delta S, but that's getting way too much, way too wordy. So in this case, a reaction will be non-spontaneous in the forward reaction if it is endothermic and the entropy is dropping, it becomes more ordered. So those are my X's. X and X. This guy is always non-spawn. Always non-spawn. I'll be using that term over and over again when we start doing some examples. And that's fine. You don't have to write spontaneous, because I don't know how anybody really knows how to spell spontaneous. All those vowels in there, E's and O's, and goodness, there might be a U in there. Sometimes I stick an I in there. It's chaos. A lot of entropy in my spelling. So let's just go with non-spawn. Look, I put the T in there. Always spawn. Don't even worry about the T. Okay, that brings us to the other two situations. And I can bring the next slide up. I know we're looking at two things at the same time. Again, let's not worry about these examples. But we say a reaction is reversible if the delta H and the delta S have the same sign. And that's because the universe is pushing them in opposite directions. One reaction is spontaneous, and then the other one is non-spontaneous. It's actually driving it in the opposite direction. So when we have a plus and a minus, right, so like we have here, the delta S is pushing it in the forward direction, the delta H is pushing it in the opposite direction, and that's reversible. And I hate reversible as well. Reversible. It's reversible. I've trained you well. There's very little laughing going on. So when you have this situation, like I said, in this case, the delta S is pushing it forward, but the positive delta H, the endothermic, is actually pushing it back in the other direction. And we've got competing reactions pushing in opposite directions. Okay? In a non-spontaneous reaction, we really have both effects pushing it towards the reactants, and so it doesn't do anything because they're being pushed towards the reactants, according to the universe. Always spontaneous is being both pushed towards the product, but with reversible, one part is pushing it towards the reactants and the other part is pushing it towards the products. So you have this continual switch back and forth between reactants and products. That's why we call it reversible. It can actually head either way. And we have the same situation here. This guy is favorable towards delta H, not favorable towards delta S, also reversible. And look, I even forgot an S in there. That's why you guys are giggling at me. Still spelled it wrong. Scribble, scribble. Also reversible. Okay? I kind of quickly went over the examples to get it to be written down, but all I have here are situations where, notice, negative, right, is the delta H. This is also less than 0 because I'm going to a more ordered state. So this is exothermic, but it's also being ordered. The universe is pushing those in opposite direction. The universe wants chaos, but wants the minimum amount of energy. So it's being pushed in opposite directions. In this case, it's endothermic. So the universe doesn't like to proceed this way. It wants to proceed back this way. And in this case here, it is got an entropy greater than 0 because it's becoming more chaotic. So it's pushing it the other way. Again, that one is reversible. All right, even though I use it as an example of non-reversible. Anyway. Okay, let's now talk about something called Gibbs free energy. As you're writing, tiny little history lesson. I talked to you about entropy and how the idea of entropy came along with the advent of steam engines very early on in the Industrial Revolution. We're talking late 1600s, early 1700s. Scientists, engineers began to realize that there was some way to quantify how much useful energy or how much kinetic energy could come out of these machines. They called it entropy. It wasn't until later on in the 1800s that a chemist decided to quantify how much energy was stored in a chemical reaction. And that brought us the term enthalpy. So enthalpy actually came after entropy. Soon after this idea, the scientist that did that, his name was Ernst. N-E-R-N-S-T. Great name. I can't even pronounce it. It's hilarious. Doesn't matter. It was very soon after that a chemist by the name of Gibbs, last name Gibbs, Willibord or something like that. Anyway, American chemist, one of the first great American-born chemists, realized that this concept of entropy and enthalpy really can be brought together to combine them in a way that provides us with a quick and easy way to determine whether a reaction is spontaneous or not. So literally putting it together. And also, by putting together the amount of heat you can get from a reaction with the amount of work you can get from a reaction, what you're actually doing is you're getting this total amount of energy that can be used to do useful things. You're actually quantifying what that chemical reaction can be used to do, whether it be heat something or move something, or in many cases, like in an engine, you heat and move something, right? You heat the gas in the piston, that gas expands, it moves the piston, and so you heat the gas, which then causes an entropy change, and it pushes the piston, and this Gibbs free energy is a measure of the maximum amount of useful work and heat energy that you can get from a chemical reaction. It totals it all up, all right? So if you're going to just use propane to heat your water for your campfire or for your camp cooking thing, then you don't care about entropy because you're just using it for the heat. You just care about the enthalpy. But if you're going to use that propane to run a car to heat the gas-air mixture and push a piston, then you need the Gibbs free energy because it's going to be a total amount of the useful work it can do and the heat. All right? So depending on what you want to do, determines which value you want to see. You do need to write this down. When you just heat water with propane for, say, a camp, you're camping, all of the expanding gases that are formed, the carbon dioxide and water, they're still dispelling its entropy. It's going into the air. The work it does when you just have a propane fire and it's not contained, goes into moving the air. You know how if you have a fire, it billows up and it moves the air up above it. So if you've got paper in the fire, all the little sparks go up in the air, right? That's the unused entropy going to move the air. So when a spark rises up out of a fire, it's the entropy that's causing that to rise up out of the fire. All right? You put that all in a little space and you try to get it to do something, you're then using that to move something. Okay, excellent. So notice, we've got our delta H, and then we put a negative in front of the term that has the delta S. Remember, a positive delta S is spontaneous. The universe likes that. But by putting a negative in front of it, we're forcing the positive delta S, to now have the same sign as the delta H. So now this term, when it's negative, the universe likes it, because we've stuck a negative in front of it. We've also multiplied it by T, the temperature in Kelvin. That gets rid of that Kelvin number on the bottom of the joules per Kelvin mole. That now brings us to the same units. Which means, if the universe likes a negative delta H, and the universe likes a positive delta S, which makes that negative, a negative plus a negative will make that negative. A negative delta G is spontaneous. So the sign for delta G is really the same as the sign for delta H when it comes to spontaneous or not. If this is positive, the universe doesn't like it, and this is negative, all right, then that negative and the negative becomes a positive, and that whole thing becomes positive, and if the delta G is positive, the universe doesn't like it, it's not spontaneous. When you have the same sign, then you have a situation where this is positive and this is negative, and you've got this situation where there's going to be a balance between which one's bigger or not. And that's how we determine whether it's spontaneous or not. Okay, let's do an example and I'll explain what I'm talking about here for all of these things. Look, okay, so there I've got the following reaction. Excellent. So you can write that question down, and then we're going to go through this whole logic. My chemical reaction is a very simple physical change. We are melting ice. We want to study ice melting. Once you have that written down, I want to bring us back to my oh-so-nice neat table here. To answer the question, is the reaction spontaneous, non-spontaneous, or reversible? We can go back to this. We can do this in a couple of ways. We can look at the signs for the delta H and the delta S, and that's what we're going to do. The second thing is we could look at the delta G if we calculated it, because we're going to be doing a delta G calculation. If, like I said, the delta H is negative and the delta S is positive, which forces that to be a negative, then in this situation, delta G will be negative. And if we have a negative delta G, it's spontaneous. So if we calculated the delta G and it was negative, we could say that's a spontaneous reaction. Okay? And we will be calculating delta G's in another couple of examples. If I go to the other extreme, the delta H is positive. That's a positive number. The delta S is negative. It's becoming more orderly. Universe doesn't like that. The negative sign on that delta S and that negative sign will make a positive. A positive and a positive will have the delta G being positive, non-spontaneous. Okay? If I have the opposing situations, I will have one of these terms being positive and the other term being negative. When they're the same sign, because of this negative here, when delta H and delta S are the same sign, one term will be negative and one term will be positive, which means one will cause the delta G to go up and the other will cause the delta G to go down. And in a perfectly reversible situation, they literally cancel each other out and the delta G is equal to 0. When the delta G is equal to 0, we have a reversible situation. The entropy is pushing it in one direction and the enthalpy is pushing it in the other direction. Okay? And same thing here, the delta G will be equal to 0. Let's go ahead and do this example. Now, it's not a very complicated one, but I need to find the delta H, and you need to get your thermodynamic data out. And just like before, we need negative, the number of moles of H2O solid, and the enthalpy of formation. And I know this is fairly heavy stuff. It's signs, it's getting the signs straight. But right now we're going back to what we've done for the last 2 days. H2O solid, I need the heat of formation for that. Somebody have that number, or am I looking for it still too? I can look for it too. Is that solid or is that liquid or gas? Do we even have solid on there? I hope we have solid. Gas. That's no fun. Why don't I have, you know what? Let's switch this around. Let's make it gas to liquid. Let's make it gas to liquid just so that we've got the numbers in there. I apologize for that. Gas to liquid. I need a better table. What do we have there for the gas? Sorry, 241. That's the 241, right? Negative 241.8. So negative the reactants plus and 1 of the liquid. 280 something? 285.8? 285.8. So going from a gas to a liquid. Sorry, I dropped the negative. So that negative and that negative make a positive. It's essentially that plus that. What do we have for a value? Yep. Negative 44 kilojoules per mole, right? And if that's the only thing that's driving our universe, spontaneous or non-spontaneous? Yeah, it's spontaneous. Universe likes that. Let's find the delta S the exact same way. You're just moving over the table to the next column. Negative. There's only one of them. I just need what that number is. Positive. There's only one of them. I just need that number. So we don't need the extra brackets there, really, I guess. What is the entropy of H2O gas? $188. 188. Nobody wants to share their numbers with me, except Jenna. Thanks. 169.69.9. 69.9. Jenna can't even speak, and she's offering up all the answers. Thank you. Remember, no negatives in those entropies, right? They're a measurement of disorder. And here I've got that big negative number and a smaller positive number. What do we get there? Yep. 118.9. What's the units for entropy? Yeah. Joules per Kelvin mole. Excellent. What does the universe think about that? Doesn't like it. Therefore, what kind of situation do we have potentially setting up here? We have a reversible situation. So if the temperature, if it's reversible, determine the equilibrium temperature. So here's A, B. To determine that, we use delta G equals delta H negative T delta S. If it's reversible, what's true about the delta G? Yep. It's 0. It's at the balance point. 0 equals delta H minus T delta S. And that 0 tells us that it is reversible. Take a look at this equation now that we have the reversible situation with delta G being 0. We know the delta H. We know the delta S. The only thing that's still there is the T, so we can find the equilibrium temperature, that temperature at which it's going in opposite directions. I'll bring this term to the other side. T delta S is equal to delta H, and therefore T is equal to delta H divided by delta S. And that's something we use over and over. That is the equilibrium temperature. And it is in Kelvin. It's always in Kelvin. Okay? There's one important thing. Note, both delta H and delta S must be in the same units. Right now I've got kilojoules and I've got joules. I need to move this guy over to make it kilojoules. That's a key part of doing this question. The delta H is negative 44 kilojoules per mole. The delta S is 0.1189 kilojoules per Kelvin mole, because I moved the decimal place over. The kilojoules are gone, the mole is gone. I have Kelvin in the denominator. That makes it come up to the top, and that gives me a unit of Kelvin. What do you got? 370? You rounded that to 2 significant digits? What, is there another, did it come up to 370 or does it have another? That's fine, 370 is fine, excellent. Look at what we determined. We determined the point at which a H2O gas exists at the same temperature of H2O liquid where it goes back and forth. This technically is the boiling point. Oh my goodness. Boiling, do I need two L's? The boiling point. All right? If I take off 273, I get about 100. I get actually 97. Yep. Yeah, it is. Yes, it has to be. I can't have negative temperature. It has to be. Negative temperature is against the rules because we're dealing with Kelvin temperature. So you can't have a negative temperature. Thank you. Determine the temperature range over which this reaction is spontaneous. Okay, this is where we have to use the logic of our table. C. All right? All right? Okay. And I've got a little bit of an explanation note to go with this at this point. For a spontaneous reaction, we need negative for the delta G, right? Make sense? For a spontaneous reaction, we need delta G to be negative. Multiple ways in which I can explain this. If we have a temperature that's really big, then this term becomes really big. Because T will be a big number, and T times whatever number that delta S will make this a big number. All right? I'm going to write that down. If T is large, then negative T delta S is large. Okay? Therefore, at large T, look at delta S for spontaneity. Okay? I'm going to write another statement about this guy here when T is small. If T is small, then negative T delta S is. You're following me with the logic here? What's it going to be if T is small? It's going to be small. Small. If T is small, then this becomes really tiny. And so we don't look at the delta S anymore, but we look at the delta H for spontaneity. Therefore, at small T, look at delta H for spontaneity. All right? Now, when I say T is big and T is small, it's big and small compared to this number right here. Because at this point, they cancel each other out and we get a G of 0 at this temperature right here. So let's take a look at this reaction. Notice, it's not spontaneous in terms of entropy. If T is big, then this term dominates. And because my reaction is non-spontaneous with entropy, this reaction will be non-spontaneous at big T, at T greater than that temperature. It's spontaneous with respect to delta H. At small temperature, this thing is going to get tiny, and it's going to become spontaneous at lower temperatures because delta H is going to dominate this, and it's going to become spontaneous. So when a question is asked, determine the temperature range in which the reaction is spontaneous, you've got to determine which one is going to dominate. In this case, it's spontaneous through H, and therefore I need a low T. At low T, delta H is, no, that's wrong. I don't know, here's what's happening. I'm at a decision-making time. And here, I'm beginning to trip over my words because I'm looking at the clock. I only have one option. I only have one option. The option is, I'm not going to get through to the end of this today. I'll finish it off tomorrow. That means, and I'm not going to kick things miles back. It means I'm moving a test to Monday. I'm moving a test to Monday. All right? That's what's happening here. That's why I'm tripping over my words, right? I'm thinking, can I get it in? Can I get it in? And I'm obviously not going to get there. So we'll do more examples tomorrow. I'm still going to finish my example, obviously, but I need to just get this out, or I'm going to be tripping over every second word I'm doing as I'm trying to multitask here. So official move has taken place. Test is now on Monday. All right? Okay? All right. Okay. That's done. Let's keep going. Okay. Let's all take a deep breath, right? Because I know what you were thinking. Whoa, there's a lot on. Friday's coming. Now that we're all relaxed again, let's think this through logically. Let me go through this one more time, all right? Just to get this through, because I do want to make sure we have this idea. And let me now take the time, which I was taking away from you when I was at decision-making time. Let's go back and let's take a look at this number right here for a moment, okay? You don't need to write down this calculation, but help me do this calculation. You don't need to write it down. If I take this number and I put it back into this equation, delta G equals negative 44, right, minus, let's put that temperature into it, 370, and let's put that number of 0.1189 in there, and please calculate that value for me. They're all negatives. Yeah, negative and negative. So they're all negatives. They're both negatives, right? You see that? Calculate that for me. And I'm hoping that you get a number where you go, huh? What do you get? What do you get?
I got negative 0.007.
All right. Now, 0.007. What really are we talking about here? No. What are we talking about? 0.007. What's the value, really? To two significant digits. It's 0, right? It's 0. The reason we get 0.007 is because we rounded this number, okay? But remember when we started our equation? Look at what I put in for delta G, 0. I then solved for T, and now I'm telling you to put the same number back in. What should I get there? 0. 0. Okay. So what does that mean? That means for the transition between gas and liquid, okay, at a temperature of 370 Kelvin, which is essentially 100 degrees, right? 273 plus 100 is 373. We have this balance point between it boiling and turning back into a liquid. That's called the boiling point. What we essentially found there was the boiling point. Okay. So what's special about this number? Well, this number is special in that it's the number that results in the spontaneous enthalpy number being exactly the same size as the non-spontaneous entropy number. This perfectly cancels out this. At that temperature, because that temperature is needed to make that delta S have the same value as this. So they cancel each other out perfectly. One is now pushing in the forward direction just as hard as the other one is pushing in the reverse. Okay? Now, if I make this number a little bit smaller now, I go to a lower temperature, then this term gets a little smaller. And because this is negative and this is negative, it's positive, right? The universe doesn't like it. But as this shrinks away and becomes really tiny as I head towards absolute 0, then this delta H is the only number that's really running the reaction. And because the delta H is negative, does the universe like that or not? Because the delta H is negative and my temperature is small, this becomes negative. It's a spontaneous reaction. Okay? When the temperature is small, this term, this chunk at the end, disappears away. And really the entropy has less of an effect. It's as if the entropy was a superhero, entropy needs temperature to dominate. And if the temperature is low, the superhero of entropy loses its superpowers. I don't know. Silliness. Enthalpy, it's like a superhero that doesn't have kryptonite. It has no effect on temperature. The enthalpy is the enthalpy, whether the temperature is high or low. It stays solid. It doesn't change. So, if the temperature is low, it's as if you ignore the entropy, because entropy doesn't have an effect on the reaction anymore. And when I say temperature is low, I mean low compared to the equilibrium temperature, below it. So if I say, let's look at low temperatures, then do you look at the entropy? No, it's wimpy at that point. So let's look at the enthalpy. Does the universe like the enthalpy? Yes. So at temperatures below this, it's a spontaneous reaction. When you have small temperatures, you look to your enthalpy for whether it's spontaneous or not, because it dominates. At temperatures above it, then the entropy grows greater, and at temperatures above it, I look at this. Is the reaction spontaneous with respect to entropy? No. So where is the reaction going to be spontaneous? Above or below this temperature? Yep. Anything below it, and that reaction happens on its own, doesn't need any help. I crank the temperature up, and the reaction shifts the other way. It actually heads back the other way. So, if you want to determine spontaneity, you need to look at which one is spontaneous. In this case, the enthalpy is spontaneous. I need low temperatures in order for that to happen. So at temperatures below 370 degrees, that reaction is happening on its own. No assistance needed. If I had a reaction that was opposite, right? The entropy is the one that's spontaneous and the enthalpy is not spontaneous, then I get the opposite effect. It would be spontaneous above those temperatures. Okay? All right? Okay. So to finish this question, and let's just do this officially, we'll finish the question. Determine the temperature range in which the reaction is spontaneous. So what I've tried to get across to you here is, to determine this answer, you look at the entropy and the enthalpy. You say to yourself, the delta H is spontaneous, so I need this thing to disappear, which means I need this to become small, which means I need the temperature to be below, and that makes it spontaneous. That's the logic you use, okay? Therefore, it is spontaneous, all right, at all temperatures if T is less than 370 Kelvin. Okay? All right? I tried to rush it. Couldn't rush it. Got to move it. Got to move that test. It's going to happen. Now, obviously, I'm not going to be able to get another example in. But you can do number 2 on this sheet. And you know what? Where it says interpret the results, you can do all of these 3 steps with number 2. I'm going to give you some time tomorrow, obviously, to work, because I'm going to tell you a few more things. I'm going to finish it off nicely. But you can do this analysis for every one of number 2. I know I've got a lot of writing on it, but the breakdown of what you need to do for the reaction is find this. If they're the same sign, right? If they're the same sign, you go through this great big long process. If they're opposite signs, you could stop. You'll say, oh, that's always spontaneous at all temperatures. I can't make it work the other way. If they're the opposite sign the other way, also, oh, that's always non-spontaneous. There's no way I can make that work. I didn't get an example of that where it was always non-spontaneous. If you have it where the signs are opposite, then your answer at B stops. Your answer at B is, no, it's not it's not reversible. It's either spontaneous or non-spontaneous at all temperatures, and you're done the question. It's only when you've got the same sign that you've got to go through the deep analysis of the reversible. I will do another example tomorrow for sure, but you do have the ability to look at these and analyze them. All right? Test officially moved to Monday. And that's okay. Nothing wrong with it. I suspected I was going to have to do it, but I wasn't sure whether I could get through it. And then at 18 after, I feel the tightening around my throat. Anyway,